Welcome, students. In our last course, we explored kinematics in a straight line, focusing on motion in one dimension. Today, we take a step further into kinematics into dimensions as part of our mechanics course. To kick off this lesson, let's take a moment to explore the key learning objectives you'll achieve by the end. How to add and subtract vectors, combining them to determine resultant directions and magnitudes, essential for solving problems in physics. You will learn also how to determine vector components from their magnitude and direction, and also how to combine components to find the original vector, a key skill in vector analysis. You will learn to analyze horizontal and vertical motions independently, a crucial approach for solving complex projectile motion problems step by step. This section explores two-dimensional motion, focusing on how objects move in both horizontal and vertical directions. Now, let's move on to the introduction of kinematics in two dimensions, where we will explore how vectors are used to analyze motion in both the horizontal and vertical directions. Most natural motion is curved and is best described by two-dimensional kinematics, which extends one-dimensional kinematics to provide deeper insights into the complexities of motion. Imagine a pedestrian navigating a 2D city grid, moving through equal-sized square blocks. Their path, though simple in structure, allows us to explore fundamental concepts of motion in two dimensions. The pedestrian's journey can be analyzed using concepts of displacement and distance. While the total distance covered is 14 blocks, the displacement is the straight line distance between the starting and ending points, forming the hypotenuse of a right triangle with sides of 9 blocks east and 5 blocks north. What is the straight line distance? Let's calculate the shortest path between the starting and ending points. The shortest distance between 2 points is a straight line. To calculate it, we use the Pythagorean theorem, a square plus b square equals c square, where c is the straight line distance. Now, let's consider another example. The helicopter's straight line path is shorter than the pedestrian's 14-block walk, with each block being square and equal in size. While the pedestrian walks 14 blocks, the helicopter takes the direct route, covering less distance. The straight line distance of 10.3 blocks is shorter than the 14 blocks walked, illustrating the concept of vector properties. In two-dimensional motion, we can break the movement into horizontal and vertical components. These components combine to give the total displacement, which is calculated using the Pythagorean theorem, especially when dealing with perpendicular vectors. Next, let's move on to an important concept in vector analysis: unit vectors and vector operations. First, let's explore unit vectors and engineering notation. To solve 2D kinematic problems, we break the motion into 1D components using vectors. Vectors have both magnitude and direction, allowing us to separate the horizontal and vertical components of motion. Vectors are represented as a or with an arrow on top. The magnitude of a vector is shown as its length, and its direction is represented by an angle, often measured relative to a reference axis. This notation helps us clearly define both the size and direction of the vector in space. In component form, a vector is written as a equals 3 units in the x direction, plus 5 units in the y direction. In magnitude direction form, this same vector is expressed as 5.83 units at an angle of 59 degrees from the x-axis, where 5.83 represents the length or magnitude of the vector, and 59 degrees indicates its direction relative to the x-axis. Now, let's discuss vector addition and subtraction. The tail of a vector is its starting point, while the head, or tip, is the final pointed end of the arrow. To add vectors, we place the tail of the second vector at the head of the first. The resulting vector, or the sum, is drawn from the tail of the first vector to the head of the second vector. This method is known as the tip-to-tail method. Now, let's move on to vector subtraction. To subtract one vector from another, we reverse the direction of the vector being subtracted. This means we place the tail of the second vector at the tip of the first vector, and then draw a new vector from the tail of the first vector to the tip of the second. This new vector represents the difference between the two original vectors. Now, let's look at adding vectors analytically. To solve vector problems analytically, we first resolve the vectors into their x and y components using trigonometry. The x component is found by multiplying the magnitude of the vector by the cosine of the angle, and the y component is found by multiplying the magnitude of the vector by the sine of the angle. To find the magnitude of the vector, we use the formula, which is the square root of the sum of the squares of the x and y components. For the angle, we use the inverse tangent of the ratio of the y component to the x component. Let's now look at the multiplication of vectors and scalars. Multiplying a vector by a positive scalar changes its magnitude, but keeps the direction. A negative scalar also reverses the direction. Division by a scalar is the inverse of multiplication. Now, we will examine projectile motion and its trajectory. Projectile motion involves objects moving under gravity's acceleration, with no air resistance. The y-component has downward acceleration, while the x-component has none. Use kinematic equations to analyze each dimension separately. Use kinematic equations for each axis individually, then combine the results with vector addition to determine the total displacement and velocity. The total displacement is found using the formula s equals the square root of x squared plus y squared. To find the angle, we use theta equals the inverse tangent of y divided by x. The total velocity is calculated as v equals the square root of vx squared plus y squared. The angle of velocity, theta v, is determined by the inverse tangent of y divided by vx. Now, let's move on to some problems and exercises. A sailor sets off from the shore in a small boat, and follows to straight paths throughout the day, 3 kilometers at 30 degrees north of east, and 5.50 kilometers at 40 degrees south of west. The question is to find the sailor's final position relative to the shore. To determine the sailor's final position relative to the shore, we break each path into its x, east-west, and y, north-south, components using trigonometry, and then sum these components to find the total displacement. Given the first path with a magnitude of 3.00 kilometers and an angle of 30 degrees north of east, we calculate the x-component as 3.00 kilometers times the cosine of 30 degrees, and the y-component as 3.00 kilometers times the sine of 30 degrees. For the second path, with a magnitude of 5.50 kilometers and an angle of 40 degrees south of west, we calculate the x-component as negative 5.50 kilometers times the cosine of 40 degrees, and the y-component as negative 5.50 kilometers times the sine of 40 degrees. Now, for the calculations, for the first path, the x-component is 3.00 kilometers multiplied by the cosine of 30 degrees, which equals to 0.598 kilometers. The y-component is 3.00 kilometers multiplied by the sine of 30 degrees, which equals 1.500 kilometers. For the second path, the x-component is negative 5.50 kilometers multiplied by the cosine of 40 degrees, which equals negative 4.213 kilometers. The y-component is negative 5.50 kilometers multiplied by the sine of 40 degrees, which equals negative 3.537 kilometers. Total components, summing the x and y components, total equals x1 plus x2, equals to 0.598 for 0.213, equals 1.615 km. Total equals y1 plus y2, equals 1.5003.537, equals to 0.037 km. Magnitude of final position, r equals, total plus total equals, 1.615, plus, minus to 0.037, equals to 0.609 plus 4.149, equals 6.758, approximately equal to 0.60 km. Direction of final position, the direction, angle relative to the x-axis, is, theta equals tan, total equals tan 1, 2.037 over 1.615, equals 51.0. Since both total and total are negative, the angle is in the third quadrant. Direction equals 180 plus 51.0, equals 231.0. Thank you. I hope you learned something new today. Stay tuned for our next session on dynamics.